So look around wherever you're sitting right now. Seriously, if you're safely able to, just take a quick glance around your space.
You're probably looking through a glass window, right?
Exactly. Or maybe you have like a ceramic coffee mug sitting on the desk next to you. And it's almost a guarantee that the building you're in or the road you might be driving on is held up by concrete. We interact with these materials constantly.
Yeah, they're everywhere.
They really are. They're so fundamental to modern life that they're practically invisible to us. But today, we're going to look right at them because those windows, that mug, and those walls represent one of the most massive, stubborn, and hidden climate challenges on the planet. Welcome to our deep dive.
It's a great starting point for us, actually, because we talk constantly about, electric cars or solar panels, but the basic physical infrastructure of our world.
The actual physical stuff we build society out of.
Right, exactly. That is arguably a much harder puzzle to solve.
And to figure out exactly how we might solve it, we're focusing today on a piece of research that caught my eye, specifically because of how grounded it is. Usually you see climate models that are purely theoretical.
Whiteboard math, basically.
Yeah, exactly. But the mission of the study we're looking at today is to uncover the real-world factory floor roadblocks to cleaning up these vital materials. The authors actually interviewed 9 industry experts.
That's 7 systems engineers and plant managers from the glass industry and 2 from the cement sector, right?
Yes, exactly. And the full title of the study is Defossilising Non-Metallic Mineral Industries: Developments in High-Temperature Heat, Hard-to-Abate Emissions, and Policy Implications.
That grounded approach is really what makes this research so compelling. I mean, the tension between what works on a clean whiteboard in a lab and what is physically and economically feasible on a gritty production line, that's the core conflict we're exploring today. And to set the stage for you listening, it really helps to understand why this study groups glass, cement, and ceramics together under the umbrella term non-metallic minerals.
Right, because they seem pretty different on the surface.
They do. But basically, these are materials we pull from the earth that aren't metals, and they share some brutally difficult manufacturing traits. Specifically, they all require extreme, sustained heat. And they all rely on complex chemical reactions at the very heart of their production.
Okay, let's unpack this, because before we can talk about fixing these industries, we need to define exactly why they're labeled as hard to abate in the first place. You mentioned extreme heat in chemistry. I want to start with the heat, because we aren't just talking about like a really hot pizza oven here.
Oh, not even close. We are talking about high temperature heat well beyond 1,000 degrees Celsius.
Wow.
Yeah, for some context, the lava flowing out of a volcano is typically around 1,000 to 1,200 degrees. These industries need to hit those temperatures and maintain them constantly.
Constantly, like they never turn the ovens off.
Never. A glass furnace operates 24 hours a day, 7 days a week, for years at a time. And historically, the only reliable, affordable way to generate that kind of sustained, massive thermal energy has been burning fossil fuels.
Mostly natural gas, I'm guessing.
Mostly natural gas, sometimes coal. So trying to replace that fire with clean energy is the first massive hurdle.
See, I would think generating volcano-level heat without fossil fuels would be the ultimate roadblock. But the study points out that the heat is actually the easier part of the problem.
It is, which is wild to think about.
It's kind of terrifying to read. The second hurdle is what we might call the invisible hurdle. The industry calls them process emissions.
Right.
These are carbon dioxide emissions that aren't coming from the fuel you burn. They're released directly from the chemical transformation of the raw materials themselves.
Precisely. And this is the part that trips people up.
Yeah, so to help you visualize this at home, think about baking a loaf of bread. It absolutely doesn't matter if you bake that bread in an old school gas oven or, a state-of-the-art 100% solar-powered electric oven.
The bread still rises.
Exactly. The yeast inside the dough is going to consume sugars, and it's going to release carbon dioxide gas as the bread rises. The chemical process itself creates the emission, regardless of how clean your power source is.
That is a brilliant analogy. And what's fascinating here is that because of this undeniable chemical reality, simply swapping out a dirty power grid for a clean power grid won't actually get these industries to zero emissions.
Right.
The study lays out some staggering numbers to illustrate this. In the cement industry, process emissions account for 60% of their total CO2 footprint.
60%. Wait, so even if your cement plant runs on pure wind energy, you're still generating more than half of the emissions you were before.
You are.
But where is the carbon actually coming from? Cement looks like, gray powder. It doesn't look like coal.
It comes from a process called the calcination of limestone. Limestone is the foundational ingredient of cement, and chemically, it's calcium carbonate.
Okay.
It has carbon and oxygen locked inside its crystal structure from millions of years ago. When you heat limestone up in a kiln to make cement clinker, you are physically forcing that rock to break apart.
Oh, wow.
Yeah, it turns into calcium oxide, which you need for the cement, and it releases the leftover carbon and oxygen as CO2 gas. You are literally unsealing a geologic vault of carbon just by making the rock hot.
So you literally cannot make the material without releasing it.
You cannot. And the study notes it's a similar story for the other materials, just with slightly lower numbers. Like in the glass industry, process emissions account for about 25% of their footprint.
Okay, so a quarter of it.
Right, and that comes from the degeneration of carbonates.
Hmm.
When you melt soda ash and limestone to make glass, they undergo a similar chemical breakdown and off-gas CO2. In the ceramics industry, it's about 16% during the firing process.
Okay, so we have two distinct nightmares here. The extreme heat and the chemistry of the rocks themselves releasing carbon.
Exactly.
Since we know the heat source is a massive issue on its own, let's zoom in on the primary focus of this study. The glass industry. How are the factory engineers actually trying to replace these massive natural gas furnaces?
Well, the engineers interviewed in the study point to a technology called full electric melting tanks, or FEMTs. They highlight this as having the absolute largest leverage for emission reduction in glass.
Okay, how does that work?
The concept is fascinating. Instead of blasting a pile of raw materials with a massive gas flame from above, you pass a massive electrical current directly through the glass melt itself.
Wait, through the liquid glass?
Yeah, liquid glass actually conducts electricity, but it resists it just enough that the electrical friction generates intense heat from the inside out.
Oh, that sounds incredibly efficient. You aren't losing heat up a chimney or anything. The material itself becomes the heating element. So if electricity offers the best leverage and the physics work, why aren't we seeing these everywhere? Like if I'm running a glass plant, I'd say let's just build a massive electric tank.
And that is exactly where the factory floor realities collide with the whiteboard theories. There are massive scaling limitations. Right now, these full electric tanks hit a physical wall at around 400 to 500 tons of production per day.
Okay, is that a lot?
For a modern industrial flat glass operation, the kind making the windows for skyscrapers, that is simply not big enough.
I don't understand the bottleneck there, though. If a 400-ton tank works, why can't you just double the size of the tank and, double the amount of electricity?
It comes down to the thermal dynamics inside the molten glass, specifically regarding the electrodes. You have to physically insert massive metal rods, the electrodes, into the tank to pass the current into the glass.
Okay, that makes sense.
Right. But in a smaller tank, you can position them to get a nice, even melt. But as you scale up into a massive industrial pool of liquid glass, placing these electrodes becomes an incredibly complex geometric puzzle.
Because the electricity doesn't flow evenly.
Exactly. When you pass that much current through a huge volume of liquid, it creates intense localized heat right around the electrodes, which drives wild convection currents in the glass.
Oh, I see.
You end up with chaotic hotspots that can literally melt the refractory brick of the tank itself. You're destroying your own equipment. And worse, you get cold spots where the glass gets clumpy and ruins the entire batch. Engineers just haven't solved the physics of evenly distributing that internal electrical heat at a massive scale yet.
Wow. So you run the risk of literally melting your own factory.
Basically, yeah.
And the study points out that even if you stick to the smaller sizes they have working now, there is a severe durability problem. A traditional combustion tank where you just burn gas might last 15 to 20 years before you have to rebuild it. But these full electric tanks, the study notes they only last 3 to 5 years.
Which completely upends the business model.
Right. If I am a plant manager, that's a massive capital expenditure or CapEx nightmare. I have to completely rebuild the core of my factory up to 4 times as often.
It's completely unsustainable financially.
So that naturally forces the industry to look for ways to keep their 20-year combustion tanks, but just change the fire inside them. Is that where alternative fuels come in?
That is the logical pivot, yeah. The study looks closely at biomethane and hydrogen. Biomethane is great because it is chemically identical to natural gas. You can pump it right into the existing burners, and the furnace doesn't even know the difference.
That sounds too easy. What's the catch?
The roadblock there is simply supply. We don't produce anywhere near enough biomethane globally from organic waste to feed an industry that requires this much continuous energy.
Which brings us to hydrogen. It feels like hydrogen is always the promised savior in these heavy industry discussions.
It is technically feasible. The study confirms you only need minor modifications to the burners to use hydrogen. But it isn't a silver bullet. Hydrogen burns hotter and faster than natural gas.
Right.
And because of that intense combustion dynamic, it causes the nitrogen in the surrounding air to oxidize. This means burning hydrogen can cause a slight increase in nitrogen oxide, or NOx, emissions.
And NOx is a major air pollutant, heavily regulated because it causes smog and respiratory issues.
Yeah.
So you solve your carbon problem, but create a completely new environmental and regulatory hurdle.
Exactly.
It really feels like the glass engineers are playing an impossible game of whack-a-mole. You try electricity, the tank breaks. You try biomethane, there isn't enough. You try hydrogen, you get smog.
It is a dizzying engineering challenge, but, as complex as the glass situation is, the cement engineers are facing an even steeper climb.
Because of the rock itself.
Yes, because as we mentioned earlier, 60% of their emissions are process emissions locked inside the limestone. Even if they figure out a magic, clean heat source, they still have millions of tons of CO2 pouring out of the material itself.
So if you can't electrify those emissions away, what do?
You have to catch them. The cement experts interviewed in this study are in total agreement on this point. Capturing the carbon, often referred to as CCUS, or carbon capture, utilization, and storage, is the only viable pathway for full emission reduction in cement.
The only way.
There is no alternative reality. You have to install a massive filtration system on the exhaust stack and literally scrub the CO2 out of the air before it hits the atmosphere.
Okay, let's talk about that scrubbing. Because the study mentions technologies like amine scrubbing, capping out at 90 to 95% efficiency. What exactly is amine scrubbing? Because it sounds like you are washing the smoke.
It is essentially a chemical sponge. You pass the dirty exhaust gas up through a tower, and you spray a liquid chemical called an amine down through it. The amine selectively binds to the CO2 molecules, grabbing them out of the air while the rest of the exhaust passes through. Then you take that CO2-rich liquid, pipe it into another chamber, and heat it up to boil the pure CO2 back out so you can compress and store it.
Wait, so you heat it up again?
Yeah, and then you recycle the liquid sponge back to the start.
That sounds incredibly energy intensive. You have to heat up a massive volume of liquid just to release the gas you just caught.
Highly energy intensive. And getting the exhaust to the scrubber in a concentrated form is a whole other headache. Right now, cement plants are trying to burn anything they can get their hands on to reduce their fossil fuel use. Reconditioned waste, sewage sludge, biomass.
Sounds messy.
It is. They are testing hydrogen blending too, but the study points out they often still have to blend in fossil fuels just to hit the required temperatures.
Right, and to make that capture process more efficient, the study mentions engineers are exploring indirect electric heating in a specific part of the plant called the calciner. Because if you use electricity there, you don't have all the dirty exhaust from burning trash mixing with the CO2 from the rock. You get a highly concentrated stream of pure CO2, which makes that chemical sponge work much better.
That is a brilliant transitional step. But the main event in cement making is the rotary kiln. That is where the material has to reach 1,450 degrees Celsius.
Oh, man.
Trying to use electricity to heat a massive spinning tube to 1,450 degrees. The study plainly states there are 0 demonstration plants currently in existence at that scale.
None. So what does this all mean for the bottom line? We are talking about retrofitting plants with untested electric kilns, powering massive chemical sponge towers, and running all of this 24/7.
The economics are sobering. Electricity already makes up about 50% of cement production costs. Fully electrifying the process and powering the carbon capture machinery would require a single cement plant to double its power grid connection.
I want to pause on that.
Yeah.
Double the power grid connection for one single factory. That is a staggering amount of local infrastructure. And if they pull that off, what does it do to the price of the actual cement?
The experts estimate that because of all these massive energy demands and new technologies, the price of low-carbon cement could jump 3 to 5 times higher than what it is today.
That makes no economic sense. I mean, if green cement looks exactly like dirty cement and holds up a bridge exactly like dirty cement, but it costs up to 5 times as much, who is going to buy it?
Nobody.
Right. If I am a construction company, I'm buying the $1 brick, not the $5 brick. How does a cement manufacturer survive making that switch without voluntarily bankrupting themselves?
Under current market conditions, they don't. And that is exactly where technology hits a wall, and we have to look beyond the factory gates. A company cannot legally or financially bankrupt itself for the climate. It violates their basic fiduciary duty to exist.
Yeah, they have to make a profit.
Which perfectly highlights the next massive hurdle. Both glass and cement have their specific internal tech problems, but they both rely on something entirely outside their control to survive the transition.
You were talking about shared infrastructure. You could invent the most advanced electric glass furnace in the world or the most efficient carbon capture unit on your cement plant. But if you don't have a local power grid capable of delivering double the electricity, or a pipeline network to physically take that captured carbon away from your factory.
You have just built an incredibly expensive paperweight.
Precisely. The study emphasizes that these sectors share a desperate need for a completely revamped backbone infrastructure. They need a massive expansion of the power grid, widespread availability of green hydrogen, and continental pipelines for CO2 transport.
Exactly.
And to really grasp how complicated this infrastructure bottleneck is, this is where the study brings the ceramics industry into the picture.
Right, ceramics. We haven't touched on them much yet. They also need extreme heat. The study notes they require 800 to 1,350 degrees Celsius for a process called solid phase sintering.
Can you clarify what sintering actually is?
Yeah.
Because the study differentiates it from glass melting.
Sintering is fascinating. When you make glass, you melt everything into a liquid puddle. When you make ceramics, like a bathroom tile or a brick, you don't want it to melt into a puddle.
Right, otherwise it's not a brick anymore.
Exactly. You heat the clay up just enough so that the individual particles fuse together at their edges while the overall shape stays solid. It's basically baking it solid. But to do that evenly across thousands of tiles requires incredibly precise distributed heat, which is very hard to do with electricity right now.
But the study points out that ceramics have a unique geographic problem compared to glass and cement, right?
Yes. Cement and glass plants are usually massive, highly centralized operations. But ceramic plants are often much smaller, and they're geographically scattered all over the place.
Yeah.
Because they're scattered, connecting them to a core shared CO2 pipeline network is a logistical nightmare. You just can't justify building a massive, expensive carbon pipeline to every single small tile manufacturer in a rural region.
And even if you could, the grid reliability is a whole other issue.
Yeah.
We talked about doubling the power grid, but for the glass industry, a stable connection is a non-negotiable prerequisite. The experts in this study were brutally clear about what happens if a glass plant loses power.
Oh, it's catastrophic.
Yeah. If the electric tank goes cold during an outage, the liquid glass inside freezes solid. And you can't just flip the switch and melt it back down. The tank is completely destroyed.
The thermal shock of cooling and reheating literally shatters the refractory bricks. You basically have to bring in jackhammers or explosives to break apart a solid block of glass and rebuild the entire facility from scratch.
Wow.
So when these industries are told they need to electrify to save the climate, they aren't just asking for green power. They are demanding a power grid that literally never, ever fails.
Here's where it gets really interesting to me. The irony of all this is almost painful. Think about it. These industries, glass, cement, ceramics, they manufacture the literal building blocks of infrastructure.
Yeah.
They make the concrete for the power plant foundations. They make the glass for the solar panels. They make the ceramic insulators that sit on high-voltage power lines. Yet, their own ability to become green is currently paralyzed by a lack of shared infrastructure.
If we connect this to the bigger picture, this shared bottleneck proves that no single industry can decarbonize in a vacuum. A cement plant cannot build a 1,000-mile CO2 pipeline by itself.
No.
A glass plant cannot upgrade the national energy grid. It requires an integrated cross-sector approach coordinated at the highest levels of government.
Which brings us perfectly to the final and maybe most important phase of this study. We've established the stubborn chemistry, the daunting physics of 1,450-degree heat, and the massive infrastructure bottlenecks. So how do the 9 industry experts interviewed here suggest governments actually fix this?
Well, they emphasize a foundational principle. Industrial policies only succeed when private industry and public institutions align their goals.
Okay.
If a government simply mandates a change without providing the economic means to survive it, the industry will just collapse, or they'll move their factories to a country with weaker laws. To prevent that, The experts strongly recommend specific financial support mechanisms.
Let's get into those mechanisms. The study highlights something called Carbon Contracts for Difference, or CCFDs. Now, I see this acronym thrown around a lot in climate finance, but mechanically, how does a CCFD actually stop a cement company from going bankrupt?
Think of it as a government safety net against market volatility. Let's say a company takes a huge risk and spends millions building a green cement plant. They need the price of carbon emissions in the market to be high so that their dirty competitors are penalized, making their expensive green cement competitive.
Makes sense.
But carbon prices fluctuate wildly. A CCFD is a contract where the government sets a fixed strike price. If the real market price of carbon drops below that strike price, the government pays the green company the difference. If it goes higher, the company pays the government back.
Okay, so it removes the fear of the unknown. It guarantees the company a stable, predictable return on their green investment, regardless of what the broader market is doing.
Exactly. It makes the project bankable. You can actually take a CCFD to a bank and get a loan to build your plant.
That's huge.
It is. And alongside that, the study advocates for the Carbon Border Adjustment Mechanism, or CBAM. This is crucial for protecting local economies. If a domestic company spends millions upgrading their plant, their cement will be more expensive. They cannot survive if a builder can just import cheap, dirty cement from a neighboring country that doesn't have environmental regulations.
Let me guess. CBAM levels the playing field.
Yes, by essentially acting as a carbon tariff. When that cheap, high-carbon cement crosses the border, the importer has to pay a tax equivalent to the carbon they emitted making it. It forces the imported product to match the price of the domestic green product.
That protects the domestic producer from being undercut.
Ah.
But protecting them isn't enough. You still have to create actual demand. You need buyers for this $5 brick.
Right.
This study talks about governments implementing green-led markets. Can you explain the mechanism behind that? Like, how does a government create a market out of thin air?
It's designed to solve the classic chicken and egg problem of new technology. No one wants to make expensive green cement because no one wants to buy it. To break that cycle, the government steps in and acts as the guaranteed first customer. They might pass a law mandating that all new public infrastructure, every taxpayer-funded highway, bridge, and government building must use 20% low-carbon cement and glass, regardless of the higher upfront price.
So government absorbs the initial sticker shock.
Right. And this early intervention is necessary to ride down the cost curve. By creating an artificial, guaranteed market first, companies have the financial security to actually build the new plants, test the new tech, and scale up.
And then prices drop.
Exactly. As they scale, their processes get more efficient and the price naturally comes down. Eventually, it gets cheap enough that organic, private market acceptance follows.
That makes total sense. You buy the first expensive prototype so the rest of us could eventually buy the cheap mass market version.
Yep.
And to help those technologies get to the prototype phase, the study also points to targeted research and development funding. We need to push low-maturity tech forward. The study highlights a real-world success here, the EU-funded Electra project. They recently achieved a major breakthrough by successfully testing a fully electrified, plasma-heated cement kiln in Sweden.
That is a massive deal because remember, the rotary kiln needs to hit 1450 degrees.
Right. I meant to ask earlier, how do you even generate 1450 degrees of electricity? You mentioned plasma heating. What does that actually mean?
Instead of a traditional electric heating element, you pass electricity through a gas until it is supercharged. The electrons actually strip away from the atoms, creating plasma, a fourth state of matter.
Like a lightsaber.
Basically, it is blisteringly hot, similar to the surface of the sun, and you can direct that plasma flame right into the kiln.
That is exactly the kind of sci-fi leap we need. But as the experts in the study repeatedly note, finding a breakthrough in a pilot plant in Sweden is step one. Step two is scaling that plasma technology across thousands of plants globally, while simultaneously building the massive power grids and CO2 pipelines to support it.
It really is the ultimate test of human engineering and global political coordination.
It gives you a profound new respect for the walls around you. To wrap up this deep dive, while the chemistry of process emissions, that baking bread reality of CO2 locked in the rock, and the physics of 1450-degree heat are deeply daunting, this study shows that the alignment of engineering innovation and smart policy offers a viable, if incredibly difficult, path forward. And if you are as fascinated by the granular details as we are, we highly recommend reading the source material yourself. Once again, the full title of the study is Defossilising Non-Metallic Mineral Industries, Developments in High-Temperature Heat, Hard-to-Abate Emissions, and Policy Implications.
Before we go, there is a broader implication to all this that the study hints at, which is really worth chewing on. If building these carbon capture networks, doubling our power grids, and laying down continental hydrogen pipelines is going to take decades and trillions of dollars, will we be forced to fundamentally change how we design our societies?
What do you mean? You think we won't be able to build them fast enough?
Well, instead of bending over backwards trying to find ways to manufacture infinite amounts of clean cement and glass, might the stubborn chemical limits of these materials force us into an era of radical recycling and architectural reuse?
Oh, wow.
We are so used to just demolishing old structures to build new ones. Perhaps the true future of the non-metallic mineral industry isn't just changing the fuel in the furnace, but creating a world where tearing down an old concrete building simply becomes a thing of the past.
A completely circular world where the concrete we have today is the only concrete we get to use tomorrow. That is a wild paradigm-shifting thought to leave you with. Thanks for joining us, and we will catch you on the next Deep Dive.